this or that compressor. Or here is something that's just likely to be encoded text. Can we detect the boundaries of that? And so on and so forth. And so it's really just about this. Before we got the DNA as the foundation for classifying species, all that an explorer could do was go out there, catch an animal, check its foot or tail or beak, and drag enough of those animals back and try to systematize what the hell they were. I mean, the whole idea of the species started before Charles Darwin with Carlos Linnaeus and others, but the very idea that, some of those things were not like the others and yet similar. So a descriptive nature of biology, a descriptive nature of classifying species, that played its role. It was useful. It helped us understand deeper things about the species. So here we are, right? We've got all of those little creatures, some of them slimy, some of them wormy, some of them, with little arms and legs. And they're crawling around in the binaries, and you pick one up, and you look at it, right? And what is it? How can you try to classify quickly what it is? Now, if you're a biologist, right, and you've caught yourself an animal, well, you know to go for the hooves, right? That will give you a large part of the classification already. Then you look at the, well, not really. Not the tail. Then you look at some other distinguishing features, and finally, I've got myself a chimera. The thing that will enable this development, we believe, is a classification, a dictionary of types. And then, once we assemble that, and we have a whole bunch of binary fragments from a whole bunch of different types of files that we think are a reasonable first cut at such a classification. Then we can apply very simple visual checks. How many wings? What length the beak? Split hoof or what? Right? So that is the purpose of what we are going to do. And for that, we need to come to an agreement what a primitive type is. So not something very long, not something very short, right? Not just your basic integer, because how do you visually recognize an integer? You can visually recognize a small integer. You can search for structs in memory that are known to contain small integers. If you're looking for your proc structures or your process structure in the Windows kernel memory to locate your rootkit, right? This is to locate process structures that shouldn't be there. But that's a different thing. These things are quite large. They may be kilobytes large. We want something smaller. On the other hand, we don't want to say that the doc file is a primitive type. Gosh, no. That thing can contain everything in the kitchen sink. We can't say that a PE file, an ELF file, is a primitive type, because, again, that thing is made out of many, many parts. So we need to make a design decision here.
So I think Sergey alluded to it. What we had to do is come up with a reasonable approximation of what is too small, what is too large, and we'll show you as the decisions as we went along the way. But one thing to think about is if you think of a simple file, there's an image file may have a header and then a payload. We consider those two different things. For example, the header we consider a data structure because maybe you want to know be able to find data structures within a file, and then the payload may be a bitmap, it may be a compressed image, and they're distinct. The header and payload are distinct. And also we had to come to grips with that many types of encryption, compression, and encoding occur in this binary jungle that's out there, zoo that's out there. And how do we incorporate that into thinking about this problem? As well as potentially artifacts, like in an image file. In a compression scheme, there may be markers or something embedded very closely, very small markers. Are they considered part of that image or that compressed block, or are they something else?
So there is a disclaimer here. Again, you can bring on any custom transformation that will completely disguise the nature of the file. However, I mean, you can pack a virtual machine that actually regenerates your file, just the same, your actual content, just the same way as Dwarf does in many of the things it does. But again, your typical shell code doesn't usually come with a virtual machine. Most of the time, it comes in XOR obfuscated, or added has the same number, or the same 2-byte or 4-byte integer added to each word of the shell code. So through those transformations, we should be able to see, and we can.
Okay, so in the paper we go into lower levels, but the highest level of this categorization is what you see on the left, the idea of these primitive types. And to think about this problem, we looked at the MIME media extensions. There's several registered, the IANA, registered media types. Some analytic tools have binary templates, and then container file formats and the like. So we took a hard look at those. This is the highest level. Again, the paper goes into significantly more detail below each of these. You can envision text getting into different encoding schemes, then each of those being different human languages, for example. And the general approach we suggest in trying to identify these things, alluding to the identifying chimera, we have the byte plot view, which we showed, obviously looking at hex and ASCII. And we also present two other, the idea of looking at a frequency histogram of the bytes, and the digraphs, the two-letter sequences, two value sequences appearing in the file. And then comparing those to dictionary of other similar structures. And this is the analytic approach, but we also suggest that you will gain insights, and with those insights, you're going to find like statistical outliers or ways these things stick out, and with those you can find automated ways to identify them. So
think of it as a bunch of antique magnifying glasses. So you're in the Beagle, you've just acquired this creature, you bring them out, and you look at it through this one looking glass and say, doesn't look like anything I know. Take out another one very quickly, again, look at it through that one and say, all I can see through that looking glass is the hoof, or a part of the tail, or that strange glowing bit. But I know what that looks like because I've seen that sort of thing before. So it's really about the visual transformations of those primitive pieces that nuke some or almost all of the structure out of what you're viewing, but make the rest look familiar, make the rest look recognizable. And biplots and digraphs in particular will be very helpful.
So as we go through these examples, I'd ask you to think about, okay, we're looking at visually what stands out, but think about how it could be done algorithmically, because ultimately the future lies in this. The people in this room don't scale all that well. So if we can capture your insights in an automated way, then there's the real power, and that can be handed off to machines to do the grunt work. So even in the text category, you can see, and with these, again, just recognize that the structure is different. And that everyone in this room, or many people in this room, could write little scripts that could identify these independently, because there's nice handles that you can get your arms around. But again, within the text arena, a great deal of diversity. So what we're going to introduce here is the idea of the digraph view. So thinking about that, if you take the word black hat, the digraphs are the first two letters, BL. The next digraph is LA. The next digraph is AC. And so BL is, lowercase bl, is 98 and 108 in US ASCII. And then LA is 108.97. And so you get these pairings, these pairs of values. And by plotting these pairs of values, you gain a quick insight into the contents of a given file or a sliding window within a file. And that's what we do, which we'll get to in a second.
So for you language aficionados, programming languages aficionados out there, this is simply a bigram model of the language that is the binary. So you can think of modeling a language as recording which word follows which word, which byte in this particular case follows which byte. And you can have a table of such pairs that you observe. They're called bigrams. And you can actually generate pseudo-English or something very close at the first glance, or at the first hearing probably, I don't know. If I start sputtering gibberish, you know that sort of a circuit switched on in my brain. So the dissociated press in Emacs, the Markov models of natural language, that is the same idea. So you record the tuples, you record the bigrams.
Okay. So just looking at ASCII text. So this is the top right is this part is just a picture of it. That's the histogram, and you can see the large values near the middle. That's the lowercase characters. The long vertical line reaching all the way to the top is the space character. We started off with text because I think everybody can kind of get their head around that pretty readily. And then this is the bigraph plot. This digraph. So this plot, this is what. This is what ASCII text looks like. This is where it falls into. What do you think that bright region in the bottom right corner is? Yeah, lowercase characters. So that's lowercase characters, pairs of lowercase characters. But you'll get to the left, you'll get uppercase and then a lowercase. So you're going to see, essentially, that's a very distinct signature. And when you're looking at a binary, this will pop out at you when you hit text. And Unicode. Okay.
Question?
Yes.
On that, did you do anything to represent the frequency of occurrence? Is it more frequent or brighter, less frequent or different?
This just shows presence on the left, yeah. And you could do that. You could color code it. For this, it's just on or off. And you have to make a decision like how far ahead do you look? Do you run the entire file through this? Then you'd have different fragment types overlapping. So we took a sliding window approach.
Yes. In fact, we do have a frequency of occurrence later for a different method.
So I'm just loading a text file now. And not all that interesting, but you can see it's got, this is just a large Project Gutenberg text file. One thing that we also have in the tool is an entropy plot. So it plots alongside the entropy. So you can see that the entropy of English text, and it corresponds with the line at the same level, is about 4.2, something like that, 0 to 8 bytes, 8 being the most random or most unpredictable. And then bitmaps. So bitmaps can exist on a file, although they're uncommon. Typically, they're compressed. Importantly, though, they can exist in memory. And when a program loads a compressed file in the memory, typically it decompresses it. And we've looked at memory dumps and things like that, and you can see the bitmaps residing in there. Now, the problem with bitmaps is that where text is a very tight knot of what you could expect statistically. Bitmaps can be anything. You could have a bitmap of white noise, or you could have a bitmap of a black square. So when you're doing this, though, common bitmaps, and that's where we have to go to commonly, what will you run into? Those show, those stand out. Yes?
Will that work with steganography?
We have a steganography example in here. I would say it'll work with some. Right? There's some very, certain naive, the example we have flips lower bits, least significant bits, that shows up. But there's some very subtle techniques in current steg. Sure? Okay, so the top right is a bitmap. Now that's not looking at it with an image viewer, that's looking at it as a byte plot. So because the window, the byte plot doesn't exactly represent, it's not an image viewer, it's looking at the raw bytes in the file. That's what it'll look like, or it can. That's the histogram for that particular bitmap. But the digraphs, particularly in normal photo